The F-102 is quite an airplane. Supersonic, highly maneuverable, and yet because of this delta wing design, high performance has been achieved with a minimum compromise with stability. Stability is one of the most important characteristics about an interceptor. The airplane itself doesn't destroy anything. Its function is to serve as a stable platform from which to launch rockets and missiles. Naturally, we want to get the platform into position as quickly as possible. Therefore, we need speed and maneuverability. The F-102A is inherently a stable airplane, but external disturbances, a sudden gust, a change of air density can cause it to oscillate in one or more of its three axes. Vertical or pitch, lateral or yaw, longitudinal or roll. In a similar manner, a bump in the road can start a car bouncing on its springs. Of course, this is controlled because the shock absorbers dampen the springing action. The pitch and yaw damper system does the same thing for the F-102A, with one very important difference. When the damper system is engaged, the sudden changes of attitude in the aircraft are compensated for essentially as soon as they begin. This is possible because a rate gyro package senses the rate of aircraft deviation about the pitch, yaw, or roll axis, thus providing a corrective signal at the instant the aircraft starts to deviate. A demodulator unit receives the AC output signals from the gyro package and modifies them to provide DC signal inputs to the pitch and yaw damper amplifiers. The resultant rate signal is amplified and sent to the hydraulic elevon package, or HEP valves, which route hydraulic power to the control surface actuators, and the surface displacement is proportional to the error signal. The gyros sense the change in aircraft attitude. Therefore, the gyro output decays, and mechanical feedback within the HEP valve repositions the surfaces. All this happens before the pilot is aware there has been a disturbance. In the manual mode of flight, the pitch and yaw corrections are superimposed on pilot control. Their authority is limited to plus or minus 1 degree of elevon. And plus or minus 6 degrees of rudder. When the pilot switches on AFCS, this system has full authority. However, these AFCS signals are routed through the damper amplifiers to permit the pitch and roll damper corrections to be summed with the full authority signals. Naturally, the pilot can override AFCS signals at any time. Both AFCS and the pitch and yaw damper systems are extremely sensitive and must be kept within close tolerances. A fractional amount of erroneous correction at high speeds can cause a large change in the attitude of the aircraft. Therefore, a tester that monitors and calibrates the signals being fed to the control surfaces is vitally important. This is an F-102A automatic controls field tester, developed by Convair. And over here are 3 damper amplifiers from an F-102A. Specifically, the tester is used to monitor signals fed to the pitch and yaw damper amplifiers by the aircraft control sensing devices, or by the preset signals supplied by the tester itself. The signals originating in the tester, which simulate the signals from the airplane, are reflected as output voltage from the damper amplifiers, and is measured in degrees of control surface deflection. The tester can be used as an aid in troubleshooting by utilizing the plug selector and pin selector. Key test points are made available for localizing trouble. and it can be used to bench calibrate damper amplifiers prior to installation on the aircraft, or when it is desirable to isolate them from the rest of the damper system. The damper amplifiers are pre-calibrated by the manufacturer, but recalibration becomes necessary whenever a major component of the control system has been changed, whenever the pilot reports that the system was erratic during flight, or during certain aircraft periodic inspections. This tester supplies preset or adjustable level signals to the input channels of the subsystems. The specific input is selected by this rotary switch, and the level adjusted by the switch directly underneath. The rotary switch at the top center of the panel makes it possible to select a channel to be tested or calibrated quickly and conveniently. This switch selects one of these plugs for testing: J1, J2, J3, J17, J45, and J105. The pin selector chooses individual circuits. The switch marked Elevon Servos is used as an aid for troubleshooting by providing a means of reversing the signal from the damper amplifier to the opposite servo valve. This procedure is valuable because it can help isolate a suspected problem area by inducing a condition in the good side of the aircraft, thereby pinpointing the faulty component. This corner contains the VTVM power supply, jacks, and lift-to-test switch for the vacuum tube voltmeter. The lower right-hand corner contains the trim servo test controls. These are the engage switches for yaw damper, pitch damper, AFCS, and trim servo, similar to those in the cockpit. Each one has a press-to-test light directly above it, and the lights will illuminate when the system is engaged. This is the meter selector knob, which selects the source of voltage or current to be monitored. The meter adjust knob varies the sensitivity of the panel meter. This is the G-limiter test control and switch. The G-limiter disengages the system if an improperly operating component subjects the airplane to an excessive G loading. Now, let's see how the unit works in a routine maintenance calibration. First, let's take a walk around the airplane and check to be sure that the control surfaces are not obstructed in any way, and see that we have proper ground support equipment available. Here is a hydraulic test unit, which supplies pressure for the aircraft's hydraulic systems. The MD3 electrical power generator is hooked up, also a cooling unit for the radar components, and a pedostatic tester to regulate and supply air pressure for the trim servo check. In addition, a protractor is used to measure rudder displacement, and dial indicators to measure elevon movement. If gauges and protractors are not available, a piece of stiff wire, which will serve as a pointer, is taped to the trailing edge of the elevon, and a 6-inch rule calibrated in hundredths is secured to the fuselage. This method is acceptable for calibrations. For speed and convenience, it is best to have 3 men to run these tests. When the tester is picked up, it has a tendency to tip because of the cables in the lid. Open it up and detach the lid completely. The heavy cables were wound in first, using the maximum diameter the lid would allow. Then the lighter cables were coiled inside the big ones, and all the plugs and sockets were placed in the center core. This short cable is for bench test power. We won't need it for these calibrations. The next one, the long one, is for connection to the 105 box in the cockpit. Next, we have 4 heavy cables, the J1, J2, J3, which is also marked J45 and used later for trim servo test, and J17. These are all identified by decals, as you can see. Each cable has a single end and a forked end, except the bench test power cable. The receptacles are also marked J1, J2, J3, J17, J45, and J105. The single ends plug into the tester. Simultaneously, the ship's harness is disconnected from the amplifier. Then, the P side of the forked cable is plugged into the amplifier, and the J side receives the ship's harness. Be sure to match each cable with its receptacle to avoid blowing an amplifier. This precaution is necessary on the tester as well. Remember that the right Aileron amplifier is on the left side, and the left amplifier is on the right side when the rack is down. The center one is the rudder amplifier. Its connection is usually color-coded red because it supplies power to the other two. All right, J1, J2, J3, J17 are all set. Now the 105 cable must be hooked up in the cockpit. We have found it's a lot easier to take the 105 box out of the instrument panel completely. The cannon plug is removed from the rear of the box. It is connected to the J side of our 105 cable, and the P side is plugged into the 105 box. Turn on electrical and hydraulic power units. Now it is important to close the circuit breakers. These are all called out in your tech order. There are 7 on the circuit breaker panel in the main wheel well, 3 in the upper electronics compartment, 3 in the nose wheel well, and 1 rudder trim in the cockpit. Put the radar switch on warm, and trim elevons and rudder for takeoff trim. The first thing we check at the tester is our power supply, to see if the 115 volt and 28 volt DC lights are on. Now, connect a vacuum tube voltmeter to the tester. The power cord plugs in, the common and signal leads go into their respective jacks. Turn the radar switch to standby. Now, to check our damper plus and minus 105 voltage. Set the VTVM to plus 300 volt DC scale. Turn the pin selector to T, place the plug selector to J2, and lift the lift to read switch. The VTVM must read 93 to 117 volts, or calibrations will be off. In the same manner, we test the damper minus 105 volts using the J3 plug. Next, we test the AFCS plus and minus 105 volts using the J17 plug and pin J. The limits here are between 100 to 110 volts. Next, we adjust our aileron position pot to null and minimize the yaw damper engage shift. Put the radar switch on warm. The elevon trim and rudder trim circuit breakers are opened. Position signal source to normal. Put the VTVM on the 1 volt DC scale. Plug selector to J2. Pin selector to J. Push the lift to read switch. If it does not read 0 volts, plus or minus 4/10 volts DC, rotate the wiper arm on the aileron position pot until the voltage comes back to 0. Now the first calibration in your -7 tech order is yaw rate. Yaw damper switch on. Signal source is set to oscillator preset. Channel selector to yaw rate. The rudder trailing edge is moving the required 1.8 inches or 4 degrees peak to peak. However, if we had to adjust it, we would turn the rudder actuator feedback adjustment on the rudder amplifier until we had the proper surface movement. Position your yaw damper switch to off. Meter selector to aircraft. And the rudder should come back to within 7/100ths of an inch of its original mid position. Now notice that the sweep hand on our meter is oscillating beyond the marks. We want to bring it up so that it just breaks the 2 marks. To do this, we use the rudder amplifier zeroing control and meter adjust knob on the tester. This will then reflect exactly the movement of the rudder. Push in the channel selector control. Wait for a thump inside the tester and turn to signal ground. You notice that the signal source switch and the channel selector are solenoid-held switches, and they cannot be moved until the oscillator signal has had time to decay. Next test, minus aileron. Yaw damper switch on, channel selector to minus aileron. The rudder trailing edge should move 1.8 inches peak to peak. With the yaw damper switch off, we get the same reading on our meter. If this channel were out of adjustment, we would calibrate using the minus aileron adjustment on the rudder amplifier. Plus aileron is done in the same manner, using the plus aileron adjustment. Now for roll rate. Yaw damper switch on, channel selector to roll rate. Rudder moves 1.8 inches peak to peak. The adjustment for lag roll rate. Yaw damper on. Channel selector to signal ground. Signal source to plus DC. The rudder trailing edge should be at the neutral position. Flip the yaw damper switch to off and read the needle on the dial. It should hit the center mark exactly. Now to adjust the roll rate. Re-engage yaw damper. Move channel selector to roll rate. The rudder should move 9/10ths of an inch to the left of the mid position, and the meter will indicate the same. Put channel selector back to signal ground. Change the signal source to minus DC. Return the channel selector to roll rate. The rudder should move 9/10ths of an inch to the other side of center. The adjustment for this channel is marked lag roll rate on the rudder amplifier. Return the channel selector to signal ground, and the rudder should return to neutral. Now for the pitch rate adjustment. Both yaw and pitch damper switches are turned on. The signal source is positioned at oscillator preset. Channel selector to pitch rate. The elevon should move 7/10ths of an inch, plus or minus 4/100ths peak to peak. Put channel selector to signal ground, and the elevons should return to within 3/100ths of an inch of their mid position. Next is full authority pitch adjustment. Turn radar switch to standby. Yaw and pitch damper switches on. Signal source at oscillator preset. Flip on AFCS. Position the channel selector to FA pitch. Elevons should move 1.4 inches, plus or minus 7/100ths of an inch, peak to peak. Turn channel selector to signal ground. Elevons should return to mid position within plus or minus 7/100ths of an inch. Next is full authority roll. Put channel selector at FA roll. This is a roll. The elevons are going in opposite directions. Again, the allowable limits are 1.4 inches peak to peak, plus or minus 7/100 of an inch. Turn to signal ground, and the elevons return to mid-position. Now the G limiter tests. First is plus G. Channel selector to accelerate. The G limiter test switch to no test. We want yaw damper on manual, pitch damper on, radar to standby, and AFCS on. Yaw at pitch damper and AFCS lights are on at the tester. Now we turn the G limit test switch to plus G, no trip position. Yaw, pitch, and AFCS stay in. Then turn to plus G trip. Pitch, damper, and AFCS kick off. We run the same test for minus G. This checks the ability of the G limiter circuit to kick off the systems to prevent possible structural damage. Next is the emergency direct manual check. When the pilot pushes this button, all switches jump back to off and disengage the systems to permit direct pilot control in an emergency. The final step in our amplifier calibration procedure is the engage shift adjustment. This is necessary to minimize rudder and elevon transient when the pitch and yaw damper systems are engaged in flight. Any surface movement over the allowable 2/100 of an inch is not acceptable. It can be reduced by turning the zeroing control on the elevon or rudder amplifiers. This check can be monitored on the tester by following the 2-7 tech order. This completes our amplifier calibrations. We unhook all the cables and move the tester up near the nose for the trim servo test. We use our J45 cable, which doubles as J3, and plug into the tester, and the trim servo controller and ship's harness in the nose wheel well. The VTVM meter is used in this test also. We position our controls on the tester to pin selector A, plug selector J45, elevon servos normal, meter selector oscillator, control unit output normal, trim servo off. Actuate the trim servo switch in the cockpit to the on position. Engage the trim servo switch on the tester. Now on your VTVM, you can read voltages on these pins A through V as called out in your tech order. With the switch in the test position, the up and down lights illuminate when the control unit output up or down relay operates. The elevator trim actuator can be functionally checked by operating it from the tester. As we mentioned before, a pitot-static tester has been connected to the pressure ratio transducer, and when 1.6 times barometric air pressure is applied to the controller, the elevons should respond by moving a maximum of 8.5 degrees up position. Since the trim servo test completes the calibrations and tests of the normal maintenance procedure, we remove the test equipment from the aircraft. Some of our troubles are created by abuse of the cables while handling, or dropping the 105 cable from the cockpit after disconnecting it, bending them too sharply, which breaks the wires inside, or using a cable as a tow rope to move the tester. Let's remember, utmost care is necessary while running the calibrations. Keep voltages and control surface deflections within the allowable limits. As we said at the beginning, an interceptor is a high-performance platform from which to launch armament. An extra tenth or even hundredth of an inch in control surface displacement can make a big difference in the attitude of the aircraft.